Okay, good morning and good afternoon, everyone. So it's my pleasure today to have Avi Per for a Q-Farm seminar. So Avi received his PhD in 2005 from Weizmann Institute of Science. He then went to for a postdoc to Gila at the University of Colorado. And after that, he went back to Israel and became a professor at Ilan University, where he's been since 2008. His group specializes in quantum optics, in particular on the topic of ultra-fast broadband squeezed light generation and detection of it for applications in quantum communication and quantum sensing. And today he's going to tell us about his recent work on that area, specifically about quantum sensing with unlimited optical bandwidth. Please, the stage is yours.
Thank you, Vahid. Thank you for inviting me. I'm very glad to discuss the things that we're doing about quantum sources and quantum applications, and specifically about using the optical bandwidth resource for doing that. I have many collaborators, but maybe in the very beginning I should mention one, which is Michael Rosenblum here at Bar Ilan, who is where many of the experiments that you will see happened in his lab. Yes, we are strong. We're very closely collaborating since I came here. We have money from the Israel Science Foundation and from, in collaboration, the NSF and BSF Israel US collaboration and other sources. And I mentioned this in the beginning because I forget at the end. Okay, so yes. So what are we talking about? Well, the main thing that we're going to talk about is we're going to talk about Homodyne, or I'm talking about, and specifically about bandwidth. So this whole talk revolves around bandwidth. And you know, people are doing, for example, Homodyne measurements for many years, and they're very effective and they're a very useful quantum tool. We'll discuss them soon. But the main thing is bandwidth. You know, if you're doing what we call standard Homodyne, then you can handle bandwidths of 100 megahertz, maybe a gigahertz. I don't know, maybe even 10 gigahertz, not really for quantum measurements, but let's assume. But the point is that you have sources in optics. What is happening here? Okay, yeah, that are much, much broader than this. And specifically, this is an example from my lab. What you see here is the spectrum of parametric down conversion or squeezed light that we generate in my lab, and it is over 100 terahertz wide. And that means that you have variation. If you think about this, if this is the bandwidth that you have, then it means that you have variations. If this is the carrier frequency, then you have variations on a time scale which is close to the carrier frequency itself. The amplitude and phase varies rapidly. And how do you handle sources like this? How do you efficiently utilize them? This is the major question that I'm going to discuss today. And honestly, so far, we are not effective at doing this. We're really using just a tiny fraction near the center. And actually, this is not to scale. It's even smaller than this. So why am I talking about bandwidth? Why do I focus on, why is it so important? And the point is that this is a resource. It's an optical resource that we should find a way to utilize. And we do this very effectively in classical physics. I don't know, I can mention the frequency comb as an example, or frequency, or WDM in communication, or whatever you want. There are so many applications where we know how to exploit the optical bandwidth that is offered to us by sources and by fibers and by other means of communication to do something useful. And let's think about this specifically in quantum communication. You know, let's think for a moment about if I have this huge bandwidth, this means that I have a very short correlation time. This means that my photons are really very short in time. So, and conceptually in quantum communication, you want to communicate with single photons, approximately. This is just the motivation, so we're not going into specific details too much. So if you have such short photons, then you could have very short bits of information. And then that means that you could have a very high, I don't know, communication rate. The problem is that you need to detect this. So this detector that sits here at the end is a problem for you because it is much, much slower. So what we do here, assuming that we have so many, so many bits, then this doesn't work because in every detection time, you can have just one photon. So even if you use clever tricks to understand in which time exactly this photon is, this is by using tricks of Franson interferometer, it doesn't really matter right now what it is if you don't know. It's just a way to measure which time bin the photon is. And then you have a little bit more information than just one bit because you know where the photon was. So you can make log 2 of n bits out of this. But the point is, look how much you lost. If you could do this, what we have on the top, if you could somehow efficiently detect, have a fast detection that will be able to handle the bandwidth, then you could have a much, much larger number of photons per second or bits per second. And the ratio of n to log n is a large number when n is large. And n can be easily 1,000,000. So 1,000,000 compared to a log of 1,000,000, there's something to be gained. Okay, another concept that is relevant here. If we think about the broadband parametric down conversion or broadband squeezed light, it is actually composed of many frequency pairs. So if we look in, if we zoom in, if this is a source coming out of a parametric oscillator, for example, then it is actually composed of many modes, of frequency modes, and those modes are entangled. So every pair of frequencies around the center is entangled to the other, and there's many of them. Actually, something like 100,000 or 1,000,000 of them in such a broad bandwidth. Now, in quantum computation, they're considered as Q modes. You can make complete cluster states out of them. And those cluster states can lead to a complete scheme of quantum computing based on what is called measurement-based quantum computing. I guess some of you know it. This is, it's beautiful. And the main thing is, look, easily 1,000,000 modes. So scaling up to 1,000,000 qubits, is it reasonable? But the point is measurement. How do we measure all of them? How do we efficiently handle this huge bandwidth? So this is where we're going into talking about quantum measurement and specifically broadband quantum measurement and what we can do with this. So yes, so I'll start with quantum measurement and then say a few things. We'll talk about continuous variables. The specific things that we measure is the quadratures of light. I'll remind you quickly what those are. And then I'll discuss how we measure them in the standard way, and then how we measure them in a broadband way. So how to be able to measure the quadratures of light with unlimited bandwidth. And then we'll discuss this, and then we'll try to look into applications. I'll specifically discuss two. One is indeed related to quantum key distribution. And the other one will be Raman spectroscopy, how we can use the methods that I'll describe in order to enhance Raman spectroscopy. And with this, we'll conclude. There are things that I won't discuss. So what I will discuss are things that are related to what we do with broadband quantum light. So these are the things that will be covered today. We do have other activities. I'll just mention it now and forget about it for later. But it is considerable, and that is we look at parametric oscillators also above threshold and look at their classical dynamics. And it's beautiful. They are, there is a unique and surprising coherent dynamics that happens when you couple parametric oscillators. You can see a situation where beating, a coherent beat is not transient, but actually it's a steady state of oscillation for coupled parametric oscillators. You can generalize this to something that we call pairwise mode locking, which generates broadband, something like a comb out of parametric oscillators, but it's not a pulse. We can discuss, consider the relation of this and the relevance for solving the Ising model. These are things that I know are done in Stanford also quite a bit, but I won't say almost anything about this. So if you're interested, you can, I don't know, email me, ask me later or whatever. And we have also activity on mode-locked lasers, pure classical physics, on the physics of them and how we can manipulate their inner structure in order to make them do things that they don't usually do. If you want a mode-locked laser to tap dance, ask me about it, I'll tell you how. But okay, so let's move in, let's jump in. This is a very well-known caricature from quite some time ago about the transition, about the quantum classical border. And you know how things are, here things are ordered and clear on the classical side and you know what is happening. And on the other side, things are a little bit fuzzy and you have a cat that is both dead and alive and some, I don't know, some maybe interference between paths. It's really nice. And let's discuss this, because when we talk about quantum measurement, you talk about the transition from one side to the other. So here they say, stop, show your classical apparatus. There's another version of this caricature, which I think is even a little bit nicer, because again, it's the same thing, but okay. So, but the main thing is that what you see here: do not cross without an amplifier. You need an amplifier in order to go from quantum to classical. You need somehow to amplify a quantum signal and take it into the classical world. So this is the heart of what we discuss. You need some gain to take you from a quantum signal to a classical. And when we think about optics, there's really only two kinds of, oh, there's noise here, so I'll make sure that it doesn't happen. I'm sorry. There are really two kinds of, two quantities that we know how to measure quantum mechanically. And one is we can count photons. You know, we can count photons using, and then the amplifier is some kind of an avalanche mechanism. You have a photon hitting a cathode. This cathode emits a single photoelectron. And then this photoelectron is amplified by some avalanche mechanism to make a large, eventually electronic pulse. So this is our gain mechanism. The other quantum quantity that we know how to measure is the quadratures, or position and momentum. So if you think about an optical and harmonic oscillator, you can talk about the location, the position, and the momentum, and those in optics are called the quadratures, Q and P, X and Y, all those are common names, but eventually they're the same thing. And we measure those by homodyne. And the transfer from quantum to classical is the homodyne gain. So this is where we're going to focus into. We're going to mainly talk about the Homodyne measurement and how it works. So a quick reminder of the classical quadratures. Well, you know, a field, an optical field is characterized by an amplitude and a phase. So it's an amplitude and a phase, but of course you can use trigonometry to just write this as a cosine term and a y term. And those x and y are just the real and imaginary part of the complex quadrature. Sorry, the complex amplitude of the field. Now, of course, those can depend on time. I mean, if I have a carrier, then the amplitude can vary with time, the phase can vary with time, and that means that the quadratures can be time dependent. And this is where we're heading very quickly. Now, just to remind you, basically I mentioned before, those quadratures are really quantum variables, and they are the position and momentum of the electric field harmonic oscillator, and therefore they are related by quantum uncertainty. And you cannot measure both of them simultaneously with arbitrary precision because there is the uncertainty limit. But of course, what you can do is squeeze one on the expense of the other. So, and those are what you have here is a squeezed coherent state. We'll talk about squeezed quantum states in a moment. And so this mechanism of squeezing is the heart of what we do. And okay, so yeah. So let's remind ourselves how the basics of a Homodyne measurement. How can we measure those position and momentum of the electric field oscillator? Or we can choose which one we want to measure. And the way we would do that, if I want to measure X, what I would need to do is to multiply by a local oscillator, which has also a cosine phase. And then if I just average this over time, it is sufficient to average over just a single period of the electric field, then of course, the cosine term will come out and the sine term will be averaged to 0. And if I want to measure the y quadrature or the momentum, all I need to do is to switch the phase of the local oscillator. So if I want to measure a quadrature, what I need is a multiplier. I need an optical mixer that will take my input, multiply it by the local oscillator with a variable phase, and give out the quadratures that I'm interested in. And this is implemented in standard optics in a very simple way. The point is that we don't have a multiplier directly. So what we do is we mix linearly on a beam splitter our input and the local oscillator. So here I have, say, the input plus the local oscillator. Here I have the input minus the local oscillator. And now we put a square law detector, a photodetector in front of this. And this measures the intensity. And this introduces the interference term, which we take out by balanced measurement. This gives out indeed the multiplication of the local oscillator and the input. So we implement a mixer by doing this. Now, the point is that the question is, how fast can these photodetectors be? How fast can they follow variations of the quadratures? And the answer is not so fast. I mean, they are the problem. And another limit is that those detectors should be ideally 100% efficient. And you really need to be close. I mean, your inefficiency allows vacuum to come back in. We'll discuss this shortly later, but remember this because it is important. So standard Homodyne is on one hand slow, and on the other hand requires highly efficient detectors. And sometimes we don't have that. I mean, what do we do if we cannot have a highly efficient detector? So a quick discussion of what happens when we have a bandwidth dependent. So if your amplitude, your complex amplitude depends on time, then this is how the field looks. And of course, that means that your that your quadratures, the real and imaginary part, are also time dependent. Let's now move from time to frequency. And if you have a real signal, then it means that in frequency it is related to pairs, it is symmetric. A real signal in time is symmetric in frequency, and imaginary signal is antisymmetric, which is what you see here. That means that every frequency of the quadrature is related to two frequencies in the field itself. And those two frequencies are symmetrically detuned around the carrier. And of course, this was classical, but you can immediately generalize this to quantum. And to write, okay, the quantum quadrature would be what we call the signal plus the idler dagger. Signal and idler are exactly those. Those are that are equally shifted sidebands around the carrier of my light. And if you take this definition of the quantum quadratures, it is a generalization of what we usually call the quadrature operators, which is A plus A dagger and A minus A dagger. And the commutation relation is okay. It behaves as it should. There may be one problem that you may worry about. Some of you may ask me about. Wait, they're not Hermitian. If you look at this, signal plus idler dagger, they're non-Hermitian operators. How can they be measured? And the point is that it is true, they are non-Hermitian, but they are measurable quantities because they have a special property. And that is that indeed X does not equal X dagger, but it commutes with it. And if they commute, then that means that you can construct Hermitian operators that can be measured. And these are X plus X dagger and X minus X dagger. And those can be measured. In what sense? They can both be measured because X and X dagger commute. So we can measure both the real part, at least conceptually, both the real part and the imaginary part of X independently. So those can be measured simultaneously, as opposed to the quadratures themselves, X and Y, that cannot, because X and Y do not commute. But those operators do. So this complex quadrature that I defined here is a measurable quantity. And I'll show you how it can be measured directly. So if we think about two-mode squeezed light, meaning that I have two frequencies, I have a signal and an idler, which means that I have a time-dependent X and a time-dependent Y. If we think about this in frequency, those are just two, as I mentioned, symmetrically detuned frequencies around the carrier. If you think about this, let's move to a co-moving frame, which is rotating at the carrier. So in that frame, the signal is shifted. One of them, the signal, let's say, is shifted up in frequency. So it is moving forward. It is running forward in that frame at a rate, which is the detuning, the difference of frequencies between those two. And there's the idler, which is detuned, red detuned, and therefore is running in the opposite direction. But if both of them have the same amplitude exactly, and if both of them have the opposite phase exactly, then what you would see is that as a function of time, they both oscillate, but the sum, the total field, has indeed a pure quadrature. So if those two fields are exactly correlated in intensity to the last photon and in phase, so that their phases are exactly opposite, the total field is a pure quadrature field. And this is something to remember. But the point is that this is usually too fast for detectors. So what people do is they use a different method to measure. They don't measure the quadrature directly because they can't. So what we usually do is we measure each one independently with a local oscillator of its own, and then look at the correlations between those two. But again, this is just looking in time of what I just told you. If you have two fields, signal and idler, then what do you have? You have a beat. If you have two frequencies, what they do is they beat. They beat at a frequency which is the difference frequency. Now, this beat can be, you see here, positive cosine, negative cosine, positive cosine, negative cosine. And in that case, it is a pure X quadrature. It can be a sign, a positive sign, a negative sign, a positive sign, a negative sign, relative to the local oscillator that we have here, and then it would be a pure Y quadrature. And the main thing is that the beat, the main problem is that the beat is too fast to detect. If this was slow enough, our detectors could follow. If those two sidebands are close to the carrier, then the beat is slow and the detector can follow. But in many cases, they are much, much too fast. So this is where we're going. And the main idea is, well, it's written here. It's too obvious right now. Replace the electrical nonlinearity with an optical one. Use a broadband optical nonlinearity for this. So let's talk about parametric amplification. And a parametric amplifier, if you think about it, that's exactly what it does. It takes your input quadrature, written in the term of the two-mode quadrature, the complex quadrature I mentioned before, and amplifies it. And it takes the imaginary quadrature and de-amplifies it. Meaning you have a parametric, oh, it says parametric oscillator, it should be parametric amplifier, it doesn't really matter. It has a pump that dictates the phase. It is the pump acts as the local oscillator that tells us which quadrature we're going to amplify and which quadrature we're going to attenuate. And what will happen is that indeed this is what will happen. One of them will be amplified, and therefore here is our measurement gain. If this parametric amplifier has sufficient gain, then the quadrature of interest will be amplified to a classical level, which can be conveniently measured. And the unwanted quadrature will be de-amplified, maybe all the way down to vacuum, or sorry, not to vacuum, to be completely squeezed, but actually I don't care. As long as it is much smaller than the measured quadrature, then it cannot really contaminate it. And the main thing is that this parametric amplifier can be very broadband. And it's all done with a single local oscillator, which is this pump of the parametric amplifier. So I'm going to tell you about an experiment where we actually did that. We measured broadband squeezed light. So this is, we have squeezed vacuum that is represented by this pair of idler and signal. Each one of them is about 55 terahertz wide, and their separation is about 100 terahertz. So that means that the beats that we have here, that the involved beats are at least of the order of 100 terahertz. There is no, the detector that will detect this doesn't exist. So this is a caricature, and we generate this in a nonlinear fiber. So we have a nonlinear fiber which we pump with a pump laser, and inside there occurs four-wave mixing, which acts as our parametric mechanism that does the parametric amplification and generates squeezed vacuum here. And then in order to measure, I just told you, what do I need to do? To put a parametric amplifier. The parametric amplifier will do the homodyne measurement for me. And this parametric amplifier is just another nonlinear fiber. And how do I vary the phase of the local oscillator here? I just take the same pump and put it back into the other fiber with a variable phase, with a phase that I control. And then in the end, all I do is just detect the intensity of the light. So we look at with the spectrometer on the spectrum of the signal and the idler, and we just analyze this. So let's see, these are results, the results that we have. And then, so what do you see? You see here the spectrum of the signal side. So I told you there's a signal side, there's an idler side. We measure only the spectrum on one side. The first thing that I want you to look at is this green line. The green line is what we call the vacuum level. What does it mean, the vacuum level? It means that what we measure is vacuum. We block the first squeezer. And then what we measure here, we see here is the vacuum level. And this is indeed, well, we see some level here. This is the amplification, parametric amplification of a vacuum. And then we let the squeezed light in, and we see, first of all, we see fringes. I'll tell you in a moment why they are there, but the important thing is that sometimes they go below the vacuum. The fact that you have an amplifier that has some noise, and now you let in input and you see less than this noise, this is something that cannot happen classically. Classically, if you have an amplifier, it cannot output anything less than its own noise. But quantum mechanically, it turns out that it can, because the noise is the amplified spontaneous emission noise is the amplified vacuum. And in this case, if you let in squeezed vacuum, then you measure the squeezed quadrature and you see less. So the fact that those, and of course, sometimes you measure the amplified, the stretched quadrature, and you see more. Now, why are there fringes? Because the phase changes along the way. There is, if I quickly go back to here, there is a filter here, and there are lenses on the way, and they introduce some dispersion. And this dispersion means that the phase of the different pairs changes. So this is just an optical effect, the fact that that the different frequencies acquire a different phase due to the dispersion of the index of refraction. And this is why you see fringes and not just a straight line. But as you see, when we flip the phase of the pump, we can flip every point in the spectrum. So we can flip from constructive to destructive, or from measuring the squeezed quadrature to measuring the stretched quadrature. And you can completely calibrate this into a pure homodyne measurement. I won't go into it. It will take too long. And we can measure something like 1.7 dB of squeezing. Well, that's completely raw measurement. There's no back calculation in here. It's not a lot. I mean, people have seen 8 and 10 and 15 dB of squeezing already. So I cannot boast this number, but this number is something to discuss because we measure over the entire 55 terahertz of bandwidth. So that is to say we can lift the bandwidth limit here. So let's think for a moment about what happened here. We started with something that it was a quantum state. It had an optical bandwidth, so it was very broadband, and it was a quantum state, so it was very sensitive to loss. If I put a beam splitter there, I introduce vacuum fluctuations, and those would interfere with. And eventually, we end up with something that is probably classical and therefore loss insensitive, and it will eventually become electrical. So it will be narrow band in the end. And then there has to be a transition between those two. And the point is, you would like to transfer from quantum to classical as early as possible. Whereas you would like to delay the transfer to lose the bandwidth as late as possible. And then, so if you think about the standard homodyne, in the standard homodyne, everything happens at the detector. At the detector is where you go from optical to electrical, and this is also where you go from quantum to classical. But when you think about this parametric homodyne that I described to you, we really open a gap. We have a parametric amplifier that amplifies the quantum quadrature that we want to measure, but it does it in the optical domain. So we already amplified the quadrature that you want to measure, but we didn't lose its bandwidth. And only when we detect it will we actually lose the bandwidth. And that means that now we can operate it on optically. And if you remember, I told you if I want to measure X, I need to measure both the real part and the imaginary part of X. Then this would probably require some splitting. How do you measure both of them at the same time? And now you can, because now the quadrature is already classical. The fact that you split it does not introduce problems. Well, it does introduce problems, but to the other quadrature, the one that you don't measure. So clearly, a parametric amplifier helps. Well, nice. By the way, Vahid, how much more time do I have? Where should I need to aim to stop?
So we have 20 more minutes
Yes.
to the official hour.
But I don't want to use all.
Oh, okay. So it's up to you. So I don't have any questions on the chat box at the moment. So
okay.
Yeah.
Okay. So I'll try to continue for something like 10 minutes and then stop for questions. So clearly a parametric amplifier helps. Now, we thought that we invented this when we discovered this. Well, to tell you the truth, we didn't. And but we didn't know that at the time. So and then we saw this beautiful paper from the Kasevich group in Stanford about quantum phase magnification, which basically does the same thing for spin squeezing in cold atoms. It's a beautiful work, and we said, but we knew this, and at the time we started fighting on publishing the paper. And then we saw, no, well, this was not the first time it was discovered, but actually this relied on an earlier theoretical paper on saying how you can approach the Heisenberg. Basically, it's the same thing. Put a parametric amplifier first, it will do good. It will help you in measuring the quadrature that you want to measure. But to be honest, I then realized that there were cases that this was discovered before. Already in 1999, it was discussed in the concept of quantum teleportation. It was, see, it's a beautiful abstract. We propose an all optical continuous variable quantum teleportation scheme based on optical parametric amplifiers. That's it. But honestly, Ralph was not the first either, because in the context of optical tomography, people discussed this using preamplification from anti-squeezing as a method to do this already in '94. This was Ulf Leonhardt and Paul. But to be honest, they were not the first either. If you take a deeper look in the paper of Carlton Caves from 1981, the paper where he first discussed quantum mechanical noise in an interferometer. This is, I don't know, this is a seminal work of the field. Then he has, in the end, a technical note, technical appendix, where he discusses, he understands this point of how do we handle inefficient detectors? What do we do with inefficient detectors? And here you see, here is the interferometer, and here is a parametric amplifier standing before the photodetector. This is old news. We didn't invent anything. But what do we have? We have bandwidth. And so that is the point. The major thing is that parametric amplification enables to cross the quantum, the classical transition over an optical bandwidth. And this is useful. Okay, all the things we mentioned. So this is useful. And now I want to very briefly show you at least one application of what we can do with this. So far, this was broadband measurement. So I'll say something, this will be just a few slides about work that we're doing recently. This is really new, nothing is published yet, about how to use multiplexed quantum key distribution to multiplex quantum key distribution in this case. A quick reminder, in quantum key distribution, we have, this is BB84. For example, you need something to represent X and 1 and 0. So we can do this. You can do this, for example, by polarization. This is 1, this is 0. Or we can do this by quadratures. So if I squeeze along the X quadrature, this would be, call it 1, and the other one we call 0. Of course, we need the other mutually unbiased basis. No, the complementary basis, which is, in this case, when we talk about polarizations, this is plus minus 45 degrees. And when we think about squeezed light, it can be the same. So I can squeeze along 0 or 90 degrees, or I can squeeze along plus minus 45 degrees. Those two situations are the same, or they represent this. And what we do, okay, let me skip this. And then now the point is, I just showed you that I can measure the squeezing angle at any frequency pair. So now what we can do is we can encode the data. Now think that we put here a shaper, meaning we open the spectrum with a grating, we shape or we change the phase of each frequency independently, and then compress everything back. And then compress everything back. And now what did we do? We can now change this angle for every frequency pair independently. So what we have here, we encode not just one channel of QKD, but many. How many? As much as you can fit in your bandwidth. So can I do this trick about multiplexing in time? No, I cannot do it in time, but I can do it in frequency. I can make many channels where each one is carrying its own quantum information, and each one can be encoded either as in this basis or in this basis. How do I decide? As we do always in BB84, we randomly decide. So Alice encodes randomly here. Bob, on the other side, he wants to measure. What will he do? He will guess. He will open the spectrum and guess a phase. For each frequency, he can guess here that the phase here is 0 and 90, or maybe the phase here is plus minus 45. He will guess, and sometimes he'll get it right, and sometimes he'll get it wrong. And then what? Put a parametric homodyne amplifier to measure in these bases, and just look at the spectrum. So let me show you how it looks. This is how the spectrum looks of an actual measurement that we do in the lab. And there are really 17 channels involved here. The center is symmetric, so the other side is, as you can see, it is symmetric. So, and here you can see that we have some channels that have high intensity. Those are encoding 1. Some channels have a low intensity. Those are encoding 0. And some are in between because they are measured in the wrong basis. And if we flip the basis, if we flip the phase, then we see that almost everything flips. Well, you see, they flip, but I don't know about the threshold. Maybe we should put the threshold. These are preliminary results, but they show exactly this concept. You can multiplex quantum data with this trick of broadband source, encode in the frequency, and then measure by parametric homodyne all the frequency components. This was with 17 channels. Since then, very recently, we moved to a more dense situation. So we already have something like 40 channels. So this is a concept, and conceptually we're limited technically only by the slow SLM and slow camera that we're using and the number of pixels that we have. So this is really what limits us to something of the order of 100 channels. We cannot do more. But conceptually, you can do 1,000,000 or 100,000. It's just how broad is your bandwidth compared to how narrow you can make your channel. So to think about 1,000 channels is reasonable. That, I think that given the time, I'll just say very, very little about. This is work that I'm very proud of, but it's how to marry squeezed light with Raman spectroscopy. I plan to speak about this more. And the main thing is we try, with Raman spectroscopy, there's a signal that you want, which is called the resonant signal. And what we know how to do is how to use squeezed light in order to enhance it. There is the non-resonant background that is a problem. It limits the sensitivity, and you would like to suppress it. And we can use squeezed light in order to suppress it, or ideally all the way down to 0 and definitely below the vacuum level, below the shot noise level. And how you can use seeding, classical stimulation, on top of the quantum gain. This is always something that is important. This was recently published, well, not so recently, but almost 2 years ago, but in this paper. So, Raman is you come with light onto a molecule, the molecule can vibrate. And now if you excite a vibration in the molecule, then you're scattering a red-shifted photon, a Stokes photon. Or if you are absorbing, from the molecule a vibration, then you will generate a blue sideband, the anti-Stokes field. Now you can think of this, look, this is really very much like four-wave mixing. So it is related to four-wave mixing, and it is obvious when we look at cars. Cars is coherent anti-Stokes Raman spectroscopy. And basically what we do is this: we pump and we generate a Stokes, and which is, as we just mentioned, but then we hit it again with the pump and we have stimulated emission back to the ground state. So this is a parametric process going up and down, up again and down. And you put in the Stokes and you measure the anti-Stokes. So this is really a four-wave mixing process, which is enhanced by the resonant Raman scattering. And this is what we do. So the main thing is that there is this non-resonant background, which is not specific, and it contributes noise. I mean, the point is that this signal is much larger than this one, but there's much more molecules. There are many more molecules that are non-resonant than those that are resonant. Suppose that you have, I don't know, a protein that is sitting in water. So there's many, many water molecules and only a few protein molecules that you would like to measure. So this can overwhelm the other. And what we want to do is to increase the resonant signal and to suppress the non-resonant background. I'll tell you very quickly how we do this. Okay, the parametric amplification we saw. So I'll jump over this and tell you, okay, what we saw so far was that a parametric amplifier can generate squeezing, and another parametric amplifier can measure it, or basically it can undo it. So, if those two have exactly the same gain but opposite quadratures, then one squeezes, the other one anti-squeezes, and you start with vacuum and you end with vacuum. So nothing happened. And this has a name. It's the SU11 interferometer. And we're not going to say anything about this. And now what we're going to do is we're going to put the Raman sample in between. The Raman sample is also a parametric amplifier. The point is that those two parametric amplifiers, the external ones, they can be strong. But the Raman sample is also a parametric amplifier, but it is weak. And we can make sure that it stands at an angle. And when it does, the effect is rotating the ellipse. So we're squeezing and then we're anti-squeezing. And if this Raman sample is not there, we'll see vacuum here. But because the Raman sample is here, the squeezing ellipse rotates, and that we can measure here after the second parametric amplifier. It's somewhat similar to what we do with polarizers. If you have two crossed polarizers, nothing passes. And if you put another polarizer in between with an angle, then you do see something. So this is the concept. And because we are getting close to the end of the meeting, then I'll just tell you that it actually works. Meaning that when you do this, you enhance the Raman signal, the spontaneous Raman signal, by the gain of the external parametric oscillator. If you want to know more, I'll send you to the paper. And so you get this. The other important thing is that you can employ the phase shift, the inherent phase shift between a resonant and a non-resonant signal to suppress the background. Because if the resonant amplifier is at 45 degrees, then the non-resonant background is at 0 degrees. Well, you know, if you remember, there's a 0 and pi over 2 phase shift. And in this case, in this picture, those are the 45 degrees. And that means that the resonant signal rotates the ellipse, but the non-resonant signal does not. And that means that by tuning the gain, I can just kill it. I can kill the non-resonant background completely by tuning the relative gain between those two amplifiers. So this is what we call the enhanced Raman black box. You see, you have the Raman sample. It is sandwiched between two parametric amplifiers, but that's it. I can look at this as a black box, and this does Raman, but enhanced. It's enhanced by the squeezing. And then you can analyze the sensitivity and see that indeed it generates sub-shot noise sensitivity so that you can improve here, and that you are not so very much sensitive to loss. So for example, you can operate pretty well with even up to 30% of loss in between. You can seed it, you can stimulate it, and then you can see that you have this quantum enhanced gain that you saw before, multiplied by the stimulation term, which is something. And indeed, you can see better than sub-shot noise sensitivity with the stimulated case as well, with a large stimulation here. Okay, I'll tell you that it is robust, but I won't explain exactly why. And to summarize, you have a way to enhance the Raman gain with squeezed light. Use the inherent phase shift between the resonant and non-resonant interaction to suppress the non-resonant background. And you can include seeding and stimulate this and enjoy both classical stimulation on top of the quantum enhancement, very much like you do in LIGO. In LIGO, you have the very strong classical signal and you add the quantum squeezing to it. So, okay, I'm not going to tell you anything about this. This is the talk that I will not give about the classical coupled parametric oscillators. If you want to learn about that, you'll need to ask Leon. Leon Bello is a really bright, this is my group. Leon is a bright PhD student. He's now finishing. He's looking for a postdoc. If somebody would like to offer a position to him, you really should, because he's really good. And he did much of the things that we discussed today. He was involved in the parametric Homodyne. Actually, the parametric Homodyne was led by Yaakov and Yoad. Those are the two students that did the experiment. Leon participated in both the theory and the experiment. Alon and Ofek did the QKD work. Yoad and Tzachi, who is not here, work on the Raman stuff. And there's much more. But with this, I'll say thank you. And we also invite postdocs. So if you know about somebody who wants to come to Israel, beautiful country, everybody's vaccinated, do come. Thanks. I'll stop.
Thank you very much, Avi, for the very interesting talk. Good. I'm gonna actually stop the recording because we're almost at the hour, but we can stay on the channel and continue with the discussions.
Okay.